History of Vector Analysis, Episode 20, Algebra of Vectors, Part 2. You are here. Hey, it's old Doc Goler. Welcome back to our investigations of the properties of modern vectors. Last time we covered vector addition and subtraction, and then we got into the dot product, which is often considered to be a form of multiplication. We will now continue by investigating the cross product. I'm going to start using a smaller font here. Remember that the charts are all available on the website if you can't read them. As usual, our first question is, are vectors commutative under the cross product operation? That is V1 cross V2 equal to V2 cross V1? Let's grind it out. V1 cross V2 is this. We get these 9 terms. Okay, I'm going to follow the same evaluation algorithm that I used for quaternions. I'm going to evaluate the ijk squared and the ijji terms using the cross product rules that Gibbs and Heaviside defined and get this, okay, which can be regrouped by ijk coefficients into this. Now let's do the same steps for V2 cross V1. We get these 9 terms, which are evaluated thusly, and which regroup into this. Are the expressions in the two boxes on this chart equal? No. Comparison shows that the two cross products are not equal. For example, in the I terms, here you get plus y1z2 minus z1y2, whereas down here you get minus y1z2 and plus z1y2. However, note that this implies that multiplying either of these I terms by -1 yields the other. That is, it appears that the cross product of V1 and V2 is anti-commutative. That is, V1 cross V2 is equal to negative V2 cross V1. In practice, when it comes to actually evaluating problems, commutative and anti-commutative are essentially equally useful. Now let's get into the messy associative property for cross products. As before, here's the statement of the problem. Is V1 cross the quantity V2 cross V3 equal to the quantity V1 cross V2 cross V3? I'll evaluate the left blue expression first, and then the right purple expression, and then we'll compare the results. It is common practice to use the matrix determinant method to do this calculation, but this approach gives the same result. Okay. V2 cross V3 is equal to this. There are only 6 terms rather than 9 because I cross I equals 0 and all that. Okay, then V1 cross this expression yields this long expression, which is evaluated like this, and is then regrouped like this. Okay, so this is the blue expression, 12 terms total. Now we evaluate the other side. V1 cross V2 equals this. This product cross V3 equals this, which yields this. Evaluate the ijk expressions, and then regroup. Okay, is the purple expression the same as the blue expression? Well, here they are, thanks to copy and paste. We can compare them in groups, the I components, the j components, and the k components. Okay, first the I components. Okay, well, the good news is that 2 of the 4 terms in each line match up. The bad news is that the other 2 do not, and they don't just differ by a minus sign. Okay, they are way different. The j components are similar, and the k components are also similar. So the answer is a hard no. Vectors are not associative under the cross product, not even close. Let's pause here for a moment. Hamilton had worked like hell to develop a quaternion system that obeyed the associative property of multiplication, even sacrificing the commutative property to get it. Now, Gibbs and Heaviside were just throwing that all away. Okay? If vectors aren't associative, then from a pure mathematics perspective, what is the point? Yes, the cross product of 2 vectors, analogous to what Tate would call the vector product of the quaternion, does not obey the associative property. If you were a mathematician at this time and you saw this, you could be excused for concluding that the cross product was pretty much useless. Okay? It has already been established that it's not very elegant. Okay? If it's not even useful, if all it produces is mathematical chaos, then what good is it? This is the kicker. Even though the cross product does not obey the associative law, it turns out that the result is not chaos. It turns out that there is another kind of structure that appears. Philosophically, in addition to mathematically, this is one of those results that can really make you question your worldviews. Okay, let me say it again. You don't get chaos, at least not in this case. Okay, A cross B cross C is not associative, but it does obey another law or rule or identity. I use these terms interchangeably here. And this is the famous back cab rule, B-A-C-C-A-B, back cab rule. While not as simple as the associative property would have been, it turns out to be essentially just as useful for practical problem solving. Not better, and certainly not as beautiful, but just as practical. Ironically, this particular identity was worked out by Tate himself before he understood how others would misuse his talents. Mathematicians to this point had discovered mathematical objects that were not rational, not positive, and not real. Here, through the back door, they were now confronted with the fact that there are other mathematical properties in addition to the familiar commutative and associative and identity properties. They didn't call them properties. Rather, the standard term for these new rules that these bizarre mathematical objects called vectors always follow is vector identities. There are actually quite a few of these vector identities. Here's a table of some of them, not only for the dot product and the cross products, but for the gradient, divergence, and curl operations as well, plus some integral identities. It is my hope that you will see these identities in a new light now. I hope that I have helped you transition from seeing these expressions as, quote, rules derived by smart people that I have to memorize, to, quote, rules that seem to hold in place of the simpler ones like the associative property worked out by people who are desperately trying to address practical needs in the face of the Industrial Revolution, but that I still have to memorize. Okay, we're not done with cross products yet. We still have to touch on the existence or lack thereof of the identity and inverse properties of cross products. Does the cross product possess an identity? That is there a vector I or some other mathematical object I such that v cross I equals v for some arbitrary vector v? The answer is another hard no. V cross I will create another vector, that's true. Okay. Quick aside, having said that, if v1 and v2 are regular vectors, aka polar vectors, then the cross product of the two is an axial vector, which is a different type of mathematical object than a polar vector, but that's a story for another time. But continuing, v cross I must be, by definition, perpendicular to both v and I, and more generally perpendicular to the plane defined by v and I. Therefore, for non-zero vectors at least, v cross any vector will point in a different direction than v, and therefore it cannot be equal to v, since equality in our vector analysis is defined as the same magnitude and the same direction. Finally, what about the inverse property for the cross product? Is there a v inverse such that v cross v inverse equals I? Okay, well, we just showed that I is not defined, so the quick answer is simply no. The inverse of an arbitrary vector v is not guaranteed to be in the set of all vectors. Still, suppose we relax our definition of I. Is there another vector in the set of vectors, let's call it w, such that the vector v cross w always falls along, say, the x-axis? That is there a w such that v cross w always equals I? Okay, this could be thought of as a sort of inverse. No, the answer is we suffer from the same problem. Unless v is in the yz plane, there is no vector that you can cross v with that will produce a vector along the x-axis. That is a special case, not a general one. So the answer is no. The inverse property is not defined for the cross product. This also implies that division is not defined for the cross product. A may be equal to b cross c, but this does not imply that you can express b as a divided by some variant of the vector c. Okay, you may remember that Tate defined a quaternion as what you get when you divide one vector by another. Tate showed that this operation could be defined if you worked in 4 dimensions. Okay? While we've only explored the dot product and the cross product here, I will add that the general rule is that division is considered undefined for vectors in general. Okay? No standalone vectors in the denominator. There are 2 points that I really want to emphasize to all of the troubled physics majors out there. The first is that you should be aware that the reason you have to learn all these vector identities, the back-cab rule and all that, is because the regular identities, the associative property, division, stuff like that, aren't valid for vectors. Okay? I'm making a big deal out of this because I think it tends to get papered over in the study of physics in particular. The fact that the cross product does not obey the associative property usually gets at most 1 sentence in a textbook, and more commonly, not even that. Okay? I think it's a big deal since vector analysis is the tool that we use to model E&M along with many other branches of physics, and every worker ought to understand how his tools do and do not work. You can see that Tate had some justification to be upset about this. Quaternions satisfied the associative property, the identity property, and the inverse property. Quaternion division is defined. Okay, none of this is true for vectors. Vectors truly are, in this sense, lousy mathematical objects. But here's the second point. In practice, the fact that the cross product doesn't obey the associative law doesn't really matter. Okay? It may matter to the mathematician, it may matter to the philosopher, it may even matter to the theologian, but at least in principle, it doesn't matter to the working physicist or engineer. The validity of the back-cab rule for vectors is no less valuable than the validity of the associative property for quaternions, complex numbers, and real numbers. Okay? I have no idea what that says about the mind of God, okay, or the human ability to understand that mind. The internal logic of the set of vectors and the back-cab rule is complete and consistent, and that's all you need to do work. Okay. Do you find this interpretation of vectors and vector identities unsatisfying, distressing, nonsensical? Okay, hey, welcome to our world. All right, that's it for this episode. Next time, I will fill in the details of how our modern vector notation became formalized, leading to, among other things, a version of Maxwell's equations that fits on a t-shirt. See you then.